Greetings everyone. I am Aisha Muskan and today we are going to learn about trusted computing and multi-level security. So today almost every sector, banking, healthcare, education, e-governance relies on digital systems. So but with more dependency comes more risk. How do we make sure our systems are reliable, secure and trustworthy? So in this video, we will explore how computers build trust from up the hardware, how sensitive data is safeguarded, and why this matters both globally and here in India. So let's dive in. Trusted computing. It is about more than just software, it's about building confidence that the system behaves correctly. It ensures that all system layers, hardware, firmware, operating system, and applications are verified and trustworthy. So the key is confidentiality, integrity, and authenticity. So if any one of these is compromised, the system cannot be fully trusted. A simple analogy, think of a skyscraper. If the foundation is weak, no matter how fancy the top floors are, the building isn't safe. In computing, the hardware is our foundation. So here in trusted computing, the trust is from the hardware up. Let's look at the chain of trust. It is central to trusted computing. Visualize a stack. Hardware at the bottom, firmware above, operating system above it, and application on top. So each layer checks the integrity of the layer above before letting it execute. So for example, if a hacker inserts a malicious bootloader, the hardware will detect the mismatch and prevent the system from booting. Trust is built from bottom up, not the other way around. So software alone cannot create full trust. It depends on verified hardware also. So let's look at the building block of it. TPM, secure boot, and attestation. So trusted computing relies on specific technologies such as the TPM, which is Trusted Platform Module, a small chip for storing cryptographic keys, digital signatures. Think of it as a personal vault for your system. And secure boot ensures only trusted firmware and OS load. Any modification triggers a halt. Measured boot records every boot stage to verify integrity. And remote attestation allows the server to check the system's trust state before sharing the sensitive information. These technologies reinforce the system's identity, making it extremely difficult for attackers to compromise it. Moving on. What's TPM? It's the silent guardian. The TPM chip is the hardware cornerstone. It enables secure encryption, digital signatures, and no tampering, which means it can detect tamperings. So for instance, BitLocker uses TPM to store encryption keys safely. TPM 2.0 is now mandatory for Windows 11 installation, and in India it's increasingly important for financial and government systems to comply with the ISO standards. The TPM shifts trust from software, which can be bypassed, to hardware-based certainty. It's like having a security guard at the entrance who never sleeps. And let's see how trust is built step by step. During system startup, here's how trust is established. The BIOS or the UEFI checks the bootloader. The bootloader checks the operating system kernel. The operating system verifies applications before running them. So at each layer, the previous layer ensures the next is unmodified. This continuous verification prevents malware from infiltrating the bootloader system process, which is where most attacks happen. And next, we are going to see about the data pyramid. Trusted computing isn't just about boot security. It also protects data at rest, in use, and in motion. So think of a pyramid with 4 layers. Access control authenticates users and grants permission. Storage security encrypts sensitive databases and cloud data. And processing security ensures computation run in isolated and secure environments. Next, the last, data foundation classifies data and manages its lifecycle. So for example, banks now use AI to monitor data access in real time, automatically flagging suspicious activity. This integration of AI and trusted hardware enhances both security and compliance. So let's dive into multi-level security. Multi-level security or MLS is based on the idea that not all data is equal. So data is classified, unclassified, confidential, secret, and top secret. The no read rule ensures users can't read data from a higher classification. And the no write down rule ensures users can't write sensitive data to a lower level. This ensures confidentiality and secrecy because users in higher level clearance, like in confidential clearance, can't access data, can't modify data in the lower level, which is unclassified level. And users in the lower level, like unclassified level clearance, can't access data of top secret level. So this ensures confidentiality. And the next model, BIBA model, this ensures integrity. So it focuses on also two rules, which is the exact opposite of the previous model: no read down and no write up. So no read down means you don't trust lower integrity data. And the no write up is users can't modify higher integrity information. So together, these models protect both secrecy and accuracy of information. And moving on, real world implementations. So MLS and trusted computing aren't theoretical, obviously. Military systems rely on MLS to protect classified data, as we have seen in many movies and series. And SE Linux and AppArmor enforce access rules on Linux systems. Intel SGX and Nitro Enclave allow secure cloud processing. So these implementations show that trusted computing extends from your laptop to even cloud data centers and national infrastructures. So let's dive into the benefits of trusted computing. Benefits include hardware-based root of trust, because trust begins at the hardware level. Strong protection against malware and tampering, because each layer verifies the next level. And high assurance of confidentiality and integrity. Easier compliance with standards. And essentially, it makes the whole system reliable, predictable, and verifiable, which is what we need. So the challenges and limitations of trusted computing include privacy concerns. TPM could allow data tracing, complex key management because of the data clearance and classifying levels, limited user control because hardware trust can't be easily overridden. Integration with legacy systems can be very difficult. So balancing security, privacy, and usability is the ongoing challenge of this. So in Indian context, cyber threats are rising rapidly in India, especially targeting finance and government networks. Combining TPM with AI secured cloud system reduces breach up to 40%. So this is critical for digital payments, e-governance, and national infrastructure. So hardware rooted trust is not just technical, it's strategic for national cybersecurity. AI and future security. AI has transformed our lives in many ways. AI is also transforming securities. It can monitor millions of events per second, detect patterns, and even predict attacks before they happen. So the next wave of trusted computing will combine AI, cloud, and hardware for self-learning adaptive systems. Essentially a security ecosystem that defends itself. So the future trends of this, looking ahead, confidential computing, even data in use is encrypted. That is confidential computing. Zero trust architecture, in which trust is never assumed. That is, by default, every user is untrustable. And hardware software co-design. This is where the trust becomes measurable. So to summarize, trusted computing builds security from hardware up. Multi-level security ensures strict control over data access. Together, they form the foundation of resilient, verifiable, and secure computing systems. Include trusted computing builds security from hardware up. Multi-level security keeps data access under strict control. So together, they form foundation of secure and verifiable computing system. Now I'll give you the practical story behind trusted computing. So why hardware matters, how attackers actually try to break it, and 3 things you can do Monday morning to make systems measurably safe. So by the end, you will have mental models and actions and not just theory. So a quick real world story, a short story, which is attackers don't always go for flashy zero-day exploits. They often aim for that one small gap, a modified firmware, a stolen signing key, or a misconfigured boot setting. Something that becomes invisible once the OS is up. So that's why trust rooted in hardware like TPM and measured boot is powerful. It prevents an attacker from quietly becoming part of the trusted stack. Think of it as putting a tamper seal on every layer of a machine, except digital seals can be cryptographically verified. Supply chain and insider threats. So, two forces make hardware trust essential, which is supply chain attacks and insider threats. Supply chain attacks insert malicious firmware before a device reaches you. So, insider threat misuses privileged accesses. Trusted computing's value is that it doesn't rely on trustworthiness of humans or vendors alone. So, it cryptographically verifies the system state. That's why organizations that combine hardware root of trust with strict change control dramatically reduce stealthy compromise windows. So, consider a finance company. They adopted TPM backed encrypted storage plus remote attestation for their branch terminals. When a terminal's boot measurements didn't match an approved baseline, the central server refused to release transaction keys. Transactions halted under remediation. So, this stopped a stealthy breach within hours rather than days. So, the takeaway is attestation turns trust into an enforceable policy and not just a hope. So the 3 immediate action checklist, which is practical values you can do right away, is enable TPM plus secure boot on all endpoints and require disk encryption. It's low friction and high payoff. So next is record baseline measurements for a small set of critical systems and enable attestation for sensitive services. Start with one app, okay? And the third is map data classification. Know where secret data lives and enforce MLS policies. These are expensive but block the most common high impact attack paths. And the human factor plus policies are security isn't only chip and code, it's people and policy. So make sure key rotation and incident playbooks exist. For example, if attestation fails, have a documented isolation and forensics flow so team can act fast. Train ops team to train attestation alerts as high priority because they often indicate an early compromise. So finally, expect AI to change the game. AI will help by spotting anomalous boot patterns and access attempts, but it will also enable more subtle attacks. The rule of thumb, use AI to augment attestation and anomaly detection, not to replace cryptographic guarantees. Hardware roots of trust plus AI detection is the strongest combo. So to wrap up, trusted computing makes system verifiable from the silicon up. MLS keeps data flowing only to the right people and practical steps. So enable TPM baseline classify get to real protection fast. To answer common Q&As, so like does TPM make privacy worse because it tracks devices? TPM stores keys and measurements locally. Attestation can be designed to disclose only proofs, not raw data. So good architectures preserve privacy while proving integrity. What about legacy hardware that lack TPM? Use software mitigations, disk encryption, HSMs in cloud, and plan a phased hardware upgrade. Prioritize critical assets first. How do we handle false positives in attestation? Maintain a small, trusted exception process and review every exception. Frequent exceptions indicate process gaps that must be remediated. So, thank you all for joining and hope you enjoyed the session.